And we're back to conclude 18-1, where we're dealing with reaction rates. So far we've investigated the effect of concentration and temperature's effect on reaction rates. Concentration will affect the sheer number of collisions, so therefore if you have more collisions you have more and faster rates. If you have fewer collisions you have a slower rate. Temperature also affects the rates of reactions by speeding up the particles so that they collide more frequently, but it can also increase the violence of the collisions, which means that more collisions will result in reaction as well. The last way that you can affect reaction rates is by adding what's called a catalyst. A catalyst will speed up a reaction, but it's not consumed. Alright, now how are they going to do this? Well, what they're going to do is they're going to lower, lost my pointer there, there we go. The way they speed up the reactions is by lowering the activation energy through changing the reaction pathway. Okay, so let's just draw a picture and maybe this will illustrate this a little bit better. Let's just say that you have a mountain. Okay, there's our mountain like so. We'll make it snow-capped. There we go, the snow that's on there. And we have a mountain climber like so. He needs to have his walking stick, and he also needs to have a hat on as he goes over the mountain. Alright, now one way to go over the mountain is to scale it over the top and then come down on the other side. And of course that's going to take a certain amount of energy. However, there may be another way to get to the other side of the mountain. Another method is by burrowing a hole or a tunnel through the middle of the mountain. And so now rather than wasting all that energy going up to the top and around, you use less energy by just going right through the mountain. It's a different pathway. It takes a different series of steps. Well, that's what a catalyst basically does to a chemical reaction. It changes the steps and lowers the required amount of energy it takes to get something done. So let's go ahead and take a look at, in terms of the diagrams, what this would look like. Okay, so let's go to our last page, where we're going to take a look at catalyzed versus uncatalyzed reactions. Once again, we're dealing with energy and reaction progress. And so we'll just do as an exothermic reaction where you start with a certain amount of reactant energy. The product energy will be lower. You have the activation energy like so, and you move on to product. Alright, and so this is the amount of energy that's normally required. So that will be our EA, uncatalyzed. However, if you change the pathway, what you do is you lower the activation energy like so. Notice that the reactants and the product energy remains the same. It's just the activation energy from here to here that has changed. So this will be EA catalyzed. And so with less energy required to produce a reaction, more collisions will result in an actual reaction. Alright, let's scroll down to the bottom and show you what that means on our distribution diagram. Let's go ahead and recreate that. We'll have our 25 degrees Celsius. It looks something like this. So again, that's our 25 degrees Celsius. We'll have our 100 degrees Celsius looking something like this. And we'll have our 0 degrees Celsius looking something like this. Now originally we had said that you might have an activation energy that was somewhere around, let's say here. So that's your activation energy uncatalyzed. I'm going to extend that blue line just a little bit further so we can illustrate our point. So at this point, at 0 degrees Celsius, only these particles can react. At 25 degrees Celsius, only these particles can react. And at 100 degrees Celsius, all of these particles will result in a reaction when they collide. All right. Now what happens when you add a catalyst is you lower the activation energy requirement. So this will be EA catalyzed. And so what that has done is at every single temperature you've added more molecules that can undergo a reaction. At 0 degrees Celsius, now all of these molecules will react. At 25 degrees Celsius, or let's go with 100 here, at 100 degrees Celsius, all of these particles can undergo a reaction. And at 25 degrees Celsius, all of these now can undergo a reaction in addition to everything that was there before. So a catalyst will lower the activation energy and therefore allow more molecules to undergo a reaction. So now let's summarize. Going back to the first page. In order for a reaction to occur, you have to break the reactant bonds from the collision of the reactant particles. However, collisions must have enough energy to overcome the activation energy to be effective and result in reaction. So how do you change that? Number one, you can control the number of collisions by changing the concentration. Number two, you can change the number of collisions and the violence of the collision by adjusting the temperature. Number three, you can lower the requirement by adding a catalyst. And we're going to take a look at all three of those when we take a look at the iodine clock reaction. We are going to adjust the concentrations, see how the rates are affected. We are going to take a look at the effect of temperature by using a reaction at a warm temperature. And we're going to take a look at a reaction at a cold temperature and see how that affects the rates of reaction. And then we're going to add a catalyst and see how that affects the reaction. That concludes 18-1. We'll see you in 18-2.